Hello, and thank you for joining IDEX Health and Science for our series on optimizing fluidics for IVD. Today's segment covers our proprietary technologies for degassing and debubbling system fluids in IVD. Today, we have a number of product experts with us from IDEX, as well as a guest, a design, engineer, and system developer. And our format for this program will be a brief overview, an introduction of the participants, followed by a roundtable discussion. That will last approximately 20 minutes, after which we'll answer questions sent in from those of you listening on the phone, and you can begin keying your questions anytime into the box provided. If you're viewing this program as an on-demand webinar, you will hear the question from the original webcast, and later in the program, we'll give you an email address to send us any questions that you may still have. We'll ask 3 quick survey questions throughout the program, and we'd like to hear from you what you're looking for on the subjects of fluidic systems and fluidic optimization. I'll take a moment now to go around the room and introduce each participant in today's webinar. You'll also see on your screen some additional details about each person's fluidic experience and product specialties. Our guest today is John Manulo. John's a mechanical engineer and system developer for several instrument platforms with more than 25 years of experience. Currently, he's the principal consultant at Fluidics Design Incorporated. Brad Bessie is the VP of Business Development for IVD at IDEX. His background includes deep familiarity with Sapphire Engineering precision dispense pumps from IDEX. Corey Phipps is our valves product manager, and he also has a lot of experience with the degassing and debubbling product lines. Darren Lewis is a scientist, and Darren manages research and technology development for IDEX Health and Science. Mechanical engineer Jeff Stokes has extensive experience designing fluid handling hardware from atmospheric liquid handling robots to UHPLC pumps and valves. Here at IDEX, Jeff leads our system integration projects. I'm Bob McCarthy, R&D Director at IDEX Health and Science. Throughout my career, I've worked in a range of instrumentation from cell culture systems to drug discovery systems in regulated environments. I'll be your moderator for all 5 segments of our series of webinars, Optimizing Fluidics for IVD. If you need to sign up for the remaining programs, one each month, visit webinar.idex-hs.com, or you can catch them for later playback, and I believe we'll have them available for download as podcasts as well. One quick note before we get started with our roundtable discussion. We want these discussions to be open and informative for the engineers who are our customers. But that said, because we deal with innovative, often patent-pending scientific technologies, we're bound by non-disclosure agreements. That means we won't be able to give you the exact name of recognizable partners or platforms. We'll just refer to them generically as a leading hematology manufacturer, for instance, or a life science assay instrument. The stories are real. The names have been changed to protect everyone. Let's ask a survey question. Do you currently use a degassing or debubbling system? So if you do degassing system or debubbling system, both or neither, please choose. As IVD evolves towards smaller volume dispensing, the accuracy of each dispense becomes ever more crucial. We've addressed it with pumps, with valves, with connections, and more recently, we've dramatically improved small volume dispensing and detection sensitivity by actively eliminating bubbles from the fluid path. So, Corey, to get this discussion rolling, the roundtable, can you briefly describe how this technology works for us?
Sure. The technology that we employ for removing bubbles and dissolved gas, which are a little different in each case, is a membrane-based technology where you draw a vacuum on one side of a membrane while running the fluid on the other side. We're able then to, depending on the nature, if it's a 2-phase system, we use a membrane that intentionally breaks up the surface tension of those bubbles and then draws the gas out into the vacuum side of the system. And if we're looking at dissolved gases, then we use a different membrane that is more efficient at pulling out the dissolved gases. In IVD, we see basically 2 different areas where debubbling becomes necessary, debubbling and degassing. One is on the sample side where you're doing your analysis and those bubbles may have issues due to inaccuracies of dispense volumes or detection problems. The other side is when you're actually doing your bulk liquid dispense, which is typically DI water, where you may have a lot of fluid going to various places in the instrument. In that case, we see a bulk degassing typically of large volumes of the liquid.
So, and how do you do the bulk degassing? Are there different types of technologies for each one from the standpoint of how would I install one in my system, for instance?
Sure. Well, typically on degassing, you're putting that degasser prior to the pump on the vacuum side of the pump, where you're pulling that liquid through. And we employ different membranes depending on what you're trying to do. For instance, we have for very high-end applications where you need the best chemical compatibility, and you're looking to remove dissolved gases, we use material like Teflon AS, for example. However, if you're going to do that for bulk degassing, say you needed to get a quarter liter per minute or something, that now becomes cost prohibitive to use that. So we'll employ a different membrane technology to get to those different applications. So it's very dependent on the flow rate you're looking for, the amount of gases you're looking to remove, and whether or not it's going to be a two-phase system.
Mm-hmm. Corey, my experience, I only had one time that I remember using a degasser in a system. And so what would drive me to put a degasser in a system now and get that extra cost of adding the degasser, plus if I don't have a vacuum pump, I have to add a vacuum pump to my system?
Well, I think what's driving more use of debubbling degassing is the reduction in volumes that we've been talking about in this series. So as you reduce the volume in the system, those bubbles now displace a larger portion of your sample or of your dispense volume, making it more and more necessary to eliminate the bubbles or remove the dissolved gas so that you don't have that problem to begin with. In the case where you're talking about where you have an existing system that's working, it may not need that additional cost for the debubbling. In fact, there's been at least one example where we're working with a customer. One of the problems we see in IVD is temperature change being a source of bubbles. And in this case, the manufacturer was actually using bulk reagent that was kept on the floor in a box, and they were then running that up to the instrument, which was, so you had a pressure drop, you're drawing against it, and then not only doing that, then running into the instrument where there was a massive temperature difference because the temperature in the instrument was enclosed, holding in the heat caused from the pumps and the other devices in there. Just by running a temperature equilibration as they brought the liquids into the system, they were able to eliminate the bubble problems and you know, maybe unfortunate for us, didn't need that debubble or degasser solution. So definitely cases where you don't need it, but as you get to these smaller volumes, you get to real necessity for very accurate dispensing. That's where this comes into play. Excellent. With that in mind, we mentioned a little bit about the difference between debubbling and degassing, and very commonly when talking to manufacturers, the bubbles are the problem we hear about. They're obvious, they're visual, you can see them very quickly. The dissolved gas is not quite as obvious or not quite at the top of mind. But in doing some work on experimental work on dispensing and obtaining very accurate dispense volumes, we learned that just removing the bubbles helps a great deal, but it doesn't eliminate the problem. If you want completely accurate dispensing, you actually do need to degas, which is a little more of a preventative measure, if you will. And removing the dissolved gases in the liquid, then you don't get those bubbles formation at all, which resulted in highly accurate dispenses, multiple dispenses in our experimentation.
Corey, is there maintenance with these?
No, there's not. In our design, these membranes are swept during the use, and there's essentially no maintenance. We do have vacuum sources that we provide that have very high mean time to failure on the vacuum pumps. However, in many cases, there's an existing vacuum source in the system, and we've worked with various customers to design and size the degassers not only just for the flow rates and things which you do normally, but also to work with the vacuum source they have in the system so that they don't add any extra cost by driving a second vacuum pump or a specific vacuum pump.
And you have different materials to meet different chemical compatibilities of the liquids?
Absolutely, we do. Yeah, everything from a Teflon AF, which is very similar to a PTFE, to we can deal with other materials with some proprietary membranes like Fluidics, and a number of things we can approach a problem with.
So I've used some of your degassers in a number of applications quite successfully. And the question I have is if you have a degasser, Corey, is that enough, or do I need to have a debubbler separate in some cases?
It depends a lot on your application. I would say in most cases the degasser is sufficient if you're able to degas your entire liquid source that's going to be in there. However, and sometimes you have a sample. If the sample is a significant volume, it may not be degassed going into the system, so you may actually want a debubbler somewhere past where the sample is going to be, just in case there is a bubble that came from that comes past there. You can remove that prior to getting to your detector or to your array where you might run into a problem.
Corey, all right, so you eliminated my bubbles. What could you prove? So what's the benefit I'm going to see from this?
It's a real hard dollar savings.
Some assays, they're so sensitive that they'll run them multiple times.
The FDA requires it, actually.
Well, yeah. I mean, like even for men with PSA, they're finding out that your PSA has to be run a couple of times because there have been so many false positives and false negatives of prostate cancer. And the PSA became the standard test for men.
But you run them 5 times, you get 5 different answers.
Yeah, exactly.
The instrument is actually designed to run multiple tests because the system currently isn't dependable that you can run one sample and get one result.
Right.
You have to run multiples to get a statistical result.
Right.
So eliminating bubbles is going to actually be able to increase the throughput, increase the reliability of the data, and decrease the cost to the customer.
And I think you have some that have some really small internal volumes, right?
We do. We can size the degassers anywhere from, I think standard product runs about 100 microliters of internal volume, upwards into the milliliters, depending on the flow rate, and it's possible to even do smaller than that if necessary.
So that is quite small.
I know that some of the customers I've run into have always been concerned about adding additional dead volume to the system, so I know that we've gotten some ways of avoiding that. Can you maybe get into describing that?
Yeah, in fact, I'll use an example. One customer we were working with had a system, an existing system, where they were running into problems when the system sat, say, over a weekend, over a time period when it wasn't being used. Temperature changes would cause microbubbles to occur all along certain length of tubing in the system.
They were having the bubble problem that was causing a 3% fallout rate. The bubbles getting to their detection where they would get false errors in their detection, instrument shut down.
And the solution that we came up for them was actually a unique patented product that we've got where we use a coaxial debubbler design where you're running the system fluid around the outside of the membrane and drawing the vacuum through the inside. So we actually essentially replace the piece of tubing and end up with a point-to-point degasser without any additional system volume being added.
Once they employed this technology, they went from 3% to 0%.
So because they're swept through, at least the ones I've used, there is no real dead volume, and it's all swept. Correct?
That's correct. Yeah, it's all swept volume in these systems, and as you mentioned, we can size. It does based a lot on the gas load and the flow rate. So, while sometimes we get a customer come in there and they want to get very small volume, 100 microliters. Well, maybe we got to come up with a little bit larger than that to take care of the problem. But we can't optimize the size of the degasser and the length, and we do have. I didn't mention specifically. We just talked a bit about this point-to-point degassing. That being opposed to the standard degassing where you have a chamber of some sort, and you can do there. So the other thing that point-to-point does is eliminate a couple of connection points that you might otherwise have that could be potential leaks.
Sorry, Kate.
Unless you were using superflangeal fittings, of course.
And we don't sell one without recommending superflangeal fittings for every connection in the system.
I so appreciate that.
Yeah, absolutely.
Another survey question. If you have dispense accuracy challenges, would degassing or debubbling be your primary choice to address this? Yes or no?
So, Corey, I have a customer who's asking me, they currently use passive debubblers. And what's the benefit, or why would they want to go to an active debubbler?
Well, the active debubbler has a couple advantages. The main one being that it's maintenance-free. Most of these passive devices are somebody has to open a cap to allow the gas to escape, or it's building up. If it goes long enough, the gas may actually re-enter the system. So in an active device with this vacuum source on there, you're actually drawing all the time, drawing that gas out of the system, doesn't require anyone to touch it, and it becomes a maintenance-free version or a maintenance-free way to achieve that. The other advantage of using an active debubber or degasser is that it doesn't matter which part of the system you put it in. There's some passive degasser debubblers out there where you have to be on the positive pressure side of the system. You can't degas it before you get to the pump, meaning if your issue is dispense inaccuracy, it doesn't help you with that. It'll take those bubbles out before they might get to your detector, but your dispense is still inaccurate because the bubble was there in your pump. Using an active degassing solution or debubbling solution, you can do that prior to the pump and eliminate those issues.
Okay, so it's hands-free, invisible to the user, never has to do any kind of maintenance or have this debubbler at the surface of the instrument for access.
That's correct.
It just works.
So the idea that you can use this under vacuum or pressure, I think, is a really big deal because you can choose where you want it in the system rather than on the inlet of a flow cell versus the outlet or on an autosampler part versus an outlet. Looks like you have a lot of flexibility.
It does. It enables a lot of flexibility in the design and enables us to take care of problems you may not be able to do with other technologies, including passive debubblers.
Corey, I have a question. What about bidirectional flow? I've seen some customers where they're, going, the flow in a certain line is going different directions, reverses direction, I should say. Are we able to handle that today, or is that? Yeah,
in our devices, the direction of flow, it doesn't make a difference. We can debubble or degas in either direction. It can change directions during that. In fact, we do have some cases where, in order to achieve what the customers are looking for, we actually have essentially stopped the flow, or if the flow is stopped by virtue of the way the system works, we can be degassing that fluid while something else is going on in the instrument, and then when the fluid starts to flow again, it's now been degassed, it's ready to go, which actually enables us to use a smaller amount of membrane to achieve the same level of degassing you might if it was running at full flow.
So like at the inlet side of a dispenser or syringe pump, where maybe they sit intermittently for a period of minutes, during that time it would actually be degassing the supply water or the supply liquid.
In contact with the membrane is degassed and ready to go, so you've got that volume ready to go.
Which is correct, and we actually gone through in some cases we can design the degasser or the debubbler specifically for that dispense volume, so that we're making sure that the volume in the syringe has already been degassed. What's waiting for the next load coming to the syringe is being degassed while it's waiting, and then you never have a bubble problem that way, and very economic solution.
Survey question. If you don't use debubbling or degassing, is cost the reason, yes or no? So, again, for IVD specifically, what do we think the future for degassing and debubbling is? Where are we going with the technology for IVD?
Well, I think one of the main areas we're looking into is the membrane technology and the material science. So we're constantly looking at new membrane technologies to handle compatibility with various different liquids, to give us more universal compatibility, reduce costs. That's one of the main areas there. Another one is also in that defined membranes with better efficiency, so that perhaps where you need a great deal of internal volume to deal with your bulk degassing, now it can be done in a much smaller volume. And the result of that is not only reducing cost, but also reducing the total amount of space that takes and allowing the instruments to continue to get smaller.
For me, I see customers coming to me looking to get higher throughput, get more samples processed per hour. And for that, I think degassing and debubbling becomes more critical because that's going to allow the Fluidics system to become more compact. We're going to have high-volume degassers to service probe wash and cuvette wash and other type of washing functions faster on the system. It's also going to allow more precise and more samples being aspirated and dispensed per hour. So the throughput of the instruments is picking up, and I think the degassing has to support that.
It's one of the enabling technologies as much as the pump is, I think. I mean, you can have the best, most precise pump in the world, and if you have a bubble in there and you're trying to dispense nanoliters, you're not going to be able to do it.
Right.
It's one of the enabling
Physics
technologies.
is just still physics. You're going to have to deal with those bubbles.
Right.
Do you think in the future you'll be able to incorporate these like as a cartridge into a manifold?
Oh, absolutely. In fact, we've done some work on that now, so that's something we can handle. In fact, we've got a product in production where we actually used the manifold as basically one end of the debubbler itself, the other end being a standard fitting. So, yeah, that's something we can do now, and we see more of that in the future, integrating them within the manifolds as well as attaching them to them.
So another component that could be integrated into a manifold, complete Fluidics system.
Absolutely.
Great. Okay, so it's time now for your questions, and thanks to those of you who have sent in questions for our Fluidic experts. Two quick introductions here first, though, for other members of our team who've just been able to join us in progress. Joe Rotter is a chemical engineer, MBA, and the product manager for Systech Degassing and Debubbling Systems. And Carl Sims is one of the inventors of the Systech Degassing and Debubbling Systems. Carl has a master's degree in analytical chemistry. Both Joe and Carl have deep experience in membrane separation technology and fluidics. All right, so we're going to switch to the questions now. First one I'm going to dish up to you, Joe. This is from our audience. Is there a quick and dirty way to test my system for bubble and gas issues?
Sure. The easiest way is always to test with a degasser in line and test without it and measure the change in instrument performance. Of course, to get a little bit harder challenge for the system, you always want to test with the saturated fluids under worst case temperature and pressure drops. So the pressure going down and the temperature coming up, causing outgassing. Then the change in instrument performance would be seen with the degasser in line or without it.
Mm-hmm. Great, thanks. Another question. In our prototype instrument, I'm mixing two reagents. Both are dissolved in water, and I don't expect a reaction to occur, but I still get bubbles. What should I look for, and what can I do about it? Carl, why don't you field this one, if you would?
Oh, this is an interesting question that comes back to concentrations and solubilities of air. For instance, some people don't realize that seawater, salt water, will contain less air than fresh water. So one of the things in mixing two reagents is to take a look at the concentration of each of the two reagents, and maybe it's a simple dilution of a salt or a dilution of some other compound. It's always good to look at that, maybe even to do it in a test tube and let it stand and see whether or not a bubble forms or bubbles form in a polypropylene test tube is a good example of how to do that. So know the system. It's also interesting to take a look at the temperatures of the incoming fluids and where they are and how they're sitting in lines. So, yes, there's a lot that we can do to help with that. We've got a lot of experience in that area.
So you're saying almost feasibility prototyping even before you decide whether you tested the degasser by just setting the fluids up in the environment they're going to be tested in, right?
Absolutely,
yeah,
absolutely.
Yeah, excellent answer. Thanks. Another one, Joe. How about you take this one? Here's the question. I get bubbles in my dispensing pumps and can't dislodge them. What should I do? So this is not in the lines, but in the dispense pumps themselves.
And it's common for us to hear this. We commonly get the response that somebody's purging their system or priming too frequently because they have a bubble problem. And degassing is a simple solution, or just correcting the issue by debubbling afterwards with one of our standard debubbler products can eliminate any bubbles that dislodge infrequently or frequently.
Mm-hmm. Here's one that's maybe a good follow-on for that too, Joe. Can the presence of gases and bubbles be an intermittent problem?
Absolutely can, because the change in dissolved gases changes with temperature and pressure. So if the environment is constantly changing for the bulk fluids, then you'll have an intermittent problem with the degassing or the formation of bubbles into the solvent dispense lines.
So you're saying even, and this is one that I thought of during this discussion, that as seasons change or ambient changes from the standpoint of heating and cooling in a building, that kind of thing, you can see some changes that you have to predict for and account for.
Absolutely, or if an instrument heats up with frequent use.
Uh-huh. I even actually heard just that some of the reagents and some of the supply lines for DI water were held in a warehouse and brought in at the last minute, and people were quite surprised at how much the dispense accuracy could change even from those fluids not being held at any kind of a predictable temperature. All right, so maybe we switch to another one. Joe, is there somewhere, here's a good one here, is there somewhere that I can visualize how a degasser or debubbler works?
Absolutely. The IDEX Health and Science website has a products tab where we've located some animation for Systech debubbler and degassing products. So if you simply go to our website, you can find that animation and understand visually how a degasser and debubbler works.
Mm-hmm. And on that website, Carl, you've actually been doing some work on that website. I kind of like it because it kind of institutionalizes some of the learning that you've had to do the hard way. Can you comment on those? Just a quick bit, when we're talking about the website.
Well, I've been writing a blog which takes us back to the history of degassing in liquid chromatography, which is an analytical chemistry application which we use our Teflon AF product in. The move into in vitro diagnostic degassing and debubbling is a lot less complicated, but it has a much higher use rate for chemicals and for reagents, and I've been addressing that as well in a portion of the blog. A third blog will come out which some of what we've discussed here today, Corey specifically, has addressed. One of the applications for a customer of ours which was quite intriguing, and they have been kind enough to provide us with the slides that they used in their internal presentations to show the success of actually degassing and debubbling their system. Mm-hmm. So it will be, stay tuned.
Yeah, excellent. All right, we're not going to let you off the hook completely there, though, Carl. A couple more questions here while we have time. Here's one. Do I have to see the bubble for them to be a problem for my system reproducibility?
Well, it depends on how far you can get your eyes into the instrument as to whether you can see, but literally no. Most circumstances, your instrument's detection systems will tell you when things are going awry, and that's very straightforward. The sensors that we use, conductivity, UV, fluorescence, etc., it's just not humanly possible for the application to accommodate that, or for a human eye to discover that. And remember, things are getting smaller.
Yeah, that's for sure. Okay, here's one more. What are some of the possible sources of bubbles and gas in an IVD system? And now I know that we've talked about a lot of them already, but any particular additional thoughts on IVD systems in particular, Carl?
IVD systems, generally the sources of bubbles come from long-term accumulation on internal passageways where you're working with hydrophobic surfaces against hydrophilic, obviously, with water. And bubbles are hydrophobic, and they form and nucleate as small particles or on crevices. Cavitation is present in most of these systems. As syringes draw in, they create cavitations, low pressure zones, temperature changes. Everything that we learned in freshman chemistry is there.
Yeah, good points. All right, one last one. We're running out of time here. If I must degas my system fluids to prevent bubble formation on my dispense pumps and the sample probe lines, how do I know what level of degassing I need? Kyle, you want to field that last one too?
Yeah, generally speaking, it's not as clear for us as it is in the field of liquid chromatography. Generally speaking, we start with the idea that we want to know the flow rate and the demand rate for the liquids in the system, is particular wash water and so on like that. You want to be around 30% residual air to 40% residual air. I believe that's somewhat accepted as an industry target. But the level that you actually need is kind of like, okay, why experiment too much? It costs almost as much to do one as the other.
Okay, great. All right, thanks. And thanks to all of you who have sent in questions. Thank you also to our panel of experts and all of you listening in. And next month, I want to point out that our live fluidic webinar surveys the most common types of valves used in IVD instrumentation. It offers guidance on design considerations to determine the best valve for a particular application. Once again, on your screen for additional questions, you can contact John Mignolo at john@fluidicsdesign.com or call him at 914-241-2048. To reach one of the participants from IDEX Health and Science, call 866-339-4888. 44653 or email customerservice.hs@idexcorp.com. For other segments in this webinar series, visit webinar.idex-hs.com. For IDEX Health and Science, I'm Bob McCarthy. Thank you all for joining us.